Alrighty, welcome back to week 21. So this past week, we finished up section 5.5, which is all about optimality conditions for a dual problem. And last time we sort of built the weak duality and the strong duality, and we proved that the dual feasible points give us a lower bound on the optimal value. So three things we're covering today is first, certificates of optimality, and then complementary slackness, and then the famous KKT conditions. But by the way, this week is actually the last week before moving on to the elements of statistical learning textbook. So I'll mention more at the end of the video about that. All right, let's do a quick refresher before we start, since everything sort of leans on that today. So of course we have the primal problem here on the left. So this is just the optimization problem that you're all familiar with. And then last week we took this primal problem and we wrote the Lagrangian form where we included the objective function along with some or the weighted constraints here in the objective function. So lambda I is a multiplier sort of writing on the inequality here, and vi is the writes on the equality constraint h of I is equal to 0. And then from the Lagrangian, we built the dual function and the dual problem as follows. So here's the dual function here, this g of lambda v, which is simply the infinitum of the Lagrangian over all the input space, x in the domain. Now to solve the dual, we want to minimize g of lambda v. Also, we said earlier that this problem is dual feasible, meaning we have some lambda v pair such that lambda is greater than 0 and lambda v is in the domain of G. Likewise, we have the primal feasible, which just means that we have some x value here and some solution that satisfies these constraints. We also saw the concept of weak duality, so that just means that if you take any possible feasible solution on the dual problem, then if you take the optimal objective value on the primal problem, the dual problem is always or must be a lower bound on the optimized value here. All right, so all this should be old news, but now let's look at this equation more closely. So let x be in the domain of the primal problem, and so f of 0x is just some value of the objective function that this function can take. And if we write this as follows, again, we didn't change anything, we just included here, then we can think about this gap here. This gap, so the difference between the left side and the right side, it's called duality gap. So what this is telling us is that, if the left side is not to 0, then this value of x is not optimal. So we say that x, this value of x is suboptimal, or in this case, epsilon suboptimal, where epsilon is exactly the value which is it's suboptimal for. So i.e., f is 0x minus p star, the optimal value, so that's equal to epsilon. Finally, it sort of localizes the optimal value of the dual function to this gap as well. Okay, so now let's think about what this means sort of operationally. So we don't need to know p star, or the optimal value of the primal problem. We don't need to know p star to know how close you are to it. You just need one feasible primal point and one feasible dual point, and a gap between their objective values bounds your error. If that gap hits 0, you're done. X is primal optimal, lambda v is dual optimal, and no further questions, are asked. Alrighty, so here's a diagram here. Again, the left side is a dual function, so we want to, sorry, I think earlier in the video I said we want to minimize this. That's wrong. We want to maximize the dual function. And so we're sort of moving, you're starting lower and then you're going forward, going up. And on the contrary, the primal objective function, we want to minimize it. So we're starting at some feasible point and we're minimizing it. Sort of the gap between these two is called a duality gap, right? So this is kind of like setting up by criteria and how you would set up your solver. So we're not going to cover sort of the algorithm to update our weights to find the actual optimal value, but just pretend that you know how to do that and you write the program. Now, how do you know when to stop? What's the stop criterion? Well, what you can do is you can define some epsilon beforehand and run your program, run your algorithm, producing a sequence of primal and dual feasible pairs. And then the moment the gap drops below your tolerance, your epsilon, stop. You have a certified epsilon suboptimal point. So this is not just a heuristic. It's not just it looks converge. So this is an actual proof. This is a rigorous demonstration that you reach sort of very, very close to the solution, at least numerically. Alrighty, so now let's go one step deeper. Now, suppose strong duality holds. So remember, weak duality always holds regardless of the properties of your optimization problem. However, that's not always the case for strong duality. Usually when conditions are nice, strong duality holds, but this is not always the case. But let's assume that it holds. That is, you can find an x value in the lambda v pair such that f of 0 is equal to g. So this is just the definition of strong duality. If we can find x star and lambda star v star and set them equal to each other, we know that, well, x and lambda v are themselves optimal. Now, what can we say about this if this is true? Well, of course, we can just plug in lambda star and v star for lambda and v respectively from the dual function here. Just plug these in. And then what we've done is we simply taken the infinitum out and we know that this point here is less than equal to this expression here. Plugging in the x star here. Now look at this carefully. Since we know these terms here are both positive, we can drop them out and say this is less than equal to f of 0 x star, right? But wait a second. We started at f of 0 x star and f of 0 x star. So that means these inequalities should really be equalities. The whole thing is equal to each other. So that's really the trick. You can think of it as squeeze, squeezing these two, whatever's inside is squeezed together. So what does this mean? It means that x star, our optimal value for the primal problem, x star minimizes the Lagrangian for lambda star and v star over all x. So this is sort of the first consequence of of this sort of squeeze argument here. Another and maybe even more important result coming from this is the fact that we use that these terms are negative, right? Sorry, I think earlier in the video I said that these terms are positive. That was a mistake. It's actually negative. That's how we're able to write this term, right? Because lambda is positive and this is always negative, and same in this term is 0. Okay. So, but since we know that these are equalities, we know that this term and this term must sum to 0. So since we know that it must sum to 0, we know that each term individually must be 0. So this is a very, very important concept. When you have strong duality and you have your optimal dual and your optimal primal, this directly implies that each of your lambda and your constraint function multiplied together must equal to 0. That means, what can we say about lambda and f if it equals to 0? Well, if lambda is not equal to 0, then that forces f to be 0. If f is 0, then if f was not 0, that forces the multiplier lambda to be 0. So just writing out here, this just spells out the complementary slackness condition. And so what a lot of solvers do is that they don't check for sort of a optimal result, they check for this condition being true. And this is another way of establishing a solution. Alrighty, so now we move on to the famous KKT conditions. So KKT conditions is really a way to put everything together that we saw. We saw the the suboptimality gap. We saw the complementary slackness. So we're going to put it all together to get sort of an all-encompassing criteria for optimal solutions. But first, we need some assumption on the constraint and objective functions themselves. So we just assume so far that these are differentiable with open domains, so they don't have closed domains. So notice we don't assume anything about convexity. We just assume that they're differentiable. Since we just showed that x star, the optimal value of x, so the optimal value of the primal problem, minimizes the Lagrangian with the lambda star and v star over x, which we just proved, that means that the gradient with respect to x must vanish at x star. So all we're doing here is taking the gradient, because they're differentiable, and we're setting the x to x star. And because we know that x star minimizes the Lagrangian at these v star and lambda star values, then we know that the gradient must equal to 0 at this location. Now, what you do is you sort of combine this equation together with primal feasible, dual feasible, and complementary slackness. And you sort of get the full KKT system. So here is the KKT conditions for the non-convex case. So I don't actually recommend memorizing every little thing. Instead, sort of think about it from a big picture. First, this first line is about primal feasible. These first two lines, these conditions must hold true for x to be feasible in the primal problem. We also have lambda must be greater than 0. Again, this is feasible for the dual problem. We also have complementary slackness, right? We just talked about. And then finally, we also have the stationary condition that this equation must hold true. So any primal dual optimal pair with a 0 duality gap, convex or not, must satisfy all these conditions here. So that's the non-convex direction. So if the problem is optimal, then it must satisfy these conditions. Now here's where it gets more interesting and maybe more powerful, and why we like convexity a lot. Really the big picture here. If the problem is convex, so that means f of I is convex and h of I is affine, the arrow reverses. It means that if these conditions hold true, then the problem is optimal. So here in the non-convex case, it was only the case in the forward direction, which was any primal dual problem which satisfies this strong duality, satisfies these conditions. But with convexity, we have both directions. Anything that satisfies these conditions is also optimal as well, along with the forward direction. So just concretely here, let's say you have some x bar, lambda bar, and v bar, which satisfies all 5 conditions here. Now the claim is that they're automatically primal and dual optimal, 0 gap, and no further argument needed. Now let me try to convince you why this is the case. So again, we start with just 3 conditions, which is that lambda is greater than or equal to 0, f is convex, and h is affine. Then we know and we've shown that the Lagrangian is convex in x, and x minimizes the Lagrangian over all x here. So x tilde is the primal feasible from the first two conditions. So plugging that in, because h of I of x tilde is 0, and these are equal to 0 by complementary slackness, everything sort of collapses. And so this is equal to f of 0 x tilde here. So of course that means there's no duality gap, and this is optimal. Alrighty, so here's a neat little diagram here. So split on non-convex problems, we have only one direction, which is that we have, if you have the optimal primal dual pair, then those KKT conditions are attained. And again, if you start with just the KKT conditions, it's not necessarily the case that you have an optimal primal dual pair. But if you do have a convex problem, then it does go in the other direction. And so these are entirely equivalent, which is the KKT conditions tell you exactly what it means for it to be optimal primal dual pair. Alright, so that concludes 5.5. We looked at certificates that tell you basically how far from optimal you are. We also explored the idea of complementary slackness. It's sort of a squeeze argument that says multipliers and constraint slacks can be both positive. And finally, we saw the KKT conditions, which is necessary always and sufficient once you have convexity. So this concludes the part of the first part of the Boyd book, which is about theory. The second and third parts are about application and algorithms, respectively. Although eventually I would like to come back and finish the rest of the book, but for now, I'm going to switch to elements of statistical learning to use sort of this optimization layer to better understand machine learning. So that's what I'm gonna do next week. So I'll start with the first chapter of the elements of statistical learning. So I hope to see you there.